Good evening, everyone. Welcome to week 12 assignment solving session. This is the last problem solving session of the course. Today I'll be discussing questions related to week 12 lecture materials and the solution to week 12 assignment problems. So let's start. The first question is the preferred structure of N-butyl lithium in ether solvent is. Option A is monomeric, option B is dimeric, option C is tetrameric, option D is hexameric. So the preferred structure for N-butyl lithium is a tetramer, and the synthesis of N-butyl lithium is done by the following reaction. And N-butyl chloride reacted with lithium will give N-butyl lithium and LiCl. And the structure exists as tetramer. In the alternate corner of a cube, lithium and N-butyl ligands will be arranged. Alternate corner will be occupied with lithium, and N-butyl groups will be on the alternate group corners as well. So the option C is the answer. Next question is the treatment of tetrameric N-butyl lithium with TMEDA, which is N-N-N-diamide tetramethyl ethane 1,2-diamine, leads to the formation of option A N-butyl lithium TMEDA 4 times, option B N-butyl lithium TMEDA 3 times, option C is N-butyl lithium TMEDA twice, and option D is N-butyl lithium TMEDA, which is a monomer. So the synthesis is N-butyl lithium in the tetrameric form react with TMEDA. It will give butyl lithium TMEDA in dimer, and the structure is and 2 the lithium will be bridged with N-butyl group. So this is the dimeric form of butyl lithium TMEDA. So the answer is option C, N-butyl lithium TMEDA twice. The next question is the reaction of SgMe2 with beryllium yields. Option A, Me2Be twice HgMe. Option B, Me2Be Hg. Option C, Me4Be and 2Hg. And option D is Me2Be and Hg. So the reaction is SgMe2 plus beryllium at 383 Kelvin give Me2Be plus Hg. So this is a method for synthesis of organoberyllium compound, and another organoberyllium compound is PH2B, and its synthesis method is 2-phenyl lithium is treated with beryllium chloride gives PH2B plus 2LiCl. So in vapor phase, Me2B is monomeric, and it's in a linear form, and in the solid state Me2B will be polymeric. So linear form is similar to BeCl2, uh, but in the solid state it's in polymeric. So beryllium gets sp3 hybridized and forms 3-center 2-electron bond with methyl bridges. So beryllium in ground state has 2s2 configuration. There is no electrons in 2p, and in excited state 1 electron from 2s excites to 2p. So the hybridization is sp3, and two vacant sp3 hybrid orbitals are present. So total 4 sp3 hybrid orbitals will be present on each beryllium. So, and there are 2 electrons in sp3 hybrid orbitals. So will be arranged like this, and 2 sp3 orbitals will be vacant in each beryllium. So the methyl group will be bridged here. So this is how the polymer form exists, and it's a 3-center 2-electron bond because the methyl group provides 1 electron. So 1 electron from methyl and 1 electron from beryllium, but there are 3 centers, Be, Me, Be. So that's a 3 center 2 electron bond. Next question is, the following reaction is an example of Al2CH3 6 times 2BF3 giving 2LF3 plus 2BCH3 thrice. Option A is transmetallation reactions. B is beta hydrogen elimination reaction. Option C is hydrometallation reaction, and option D is metathesis reaction. So in transmetallation, one metal take place of another. So example is magnesium treated with RMgBr or HgGr. So it will be forming Hg plus RMgBr. So here magnesium replaces mercury. So RHgBr becomes RMgBr. And another reaction is again magnesium plus R2Hg. So here magnesium replaces mercury. So Hg plus R2Hg. And in beta hydrogen elimination reaction, it takes place when there is hydrogen present in the carbon at beta position of metal. So there should be a beta hydrogen present. In this reaction, there is no beta hydrogen. So the example is LNM CH2CH3. So this is the alpha carbon, which is directly connected to metal, and this will be the beta carbon. And we can rewrite it as LNM CH2 CH2H. So we rewrite CH3 as CH2H. So the elimination will be this LMCH2 bond breaks, and this hydrogen will be abstracted by M. So an alkene is formed along with the metal hydride. So it will be LNMH plus CH2 double bond CH2. So this is the beta hydrogenation elimination. An unsaturated bond is formed along with metal hydride. In hydromethylation, it's driven by the high strength of EC bond relative to that of most EH bonds, and occur with a wide range of compounds containing EH bonds. And E can be boron or silicon. So it in hydromethylation reaction, EC bond formation and EH breaking. Examples are hydroboration and hydrosilylation. So hydroboration is BH. Reacting with alkene. So this OR will be removed, and BH bond breaks and BC bond formation takes place. So it will be BH2C, and this C has 2 hydrogen, and the hydrogen that's removed from boron will be given to the next carbon. So that carbon will be having 3 hydrogen after the reaction. So this is hydroboration. And in hydrosilylation, the reaction is SiH4 reacting with the alkene will give in the presence of H2PtCl2 and 2-propanol. It forms so this SiH bond breaks and bond with this silicon and this carbon forms. This hydrogen is given to this carbon. So Si3 SiH3 C and 2 hydrogens and C2H5 and 2 hydrogens. So this is hydrosilylation. And in metathesis, reaction of an organic compound in the form of Mr reacting with the binary halide EX giving MX plus ER. So the ligands on metal will be replaced and exchanged with another binary halide. So here the halogen from E will be promoted to metal and the R from metal will be given to E. So Mx plus Er will be formed. So in the example is Li for CH3 4 times plus SiCl4 give 4 SiCl plus uh, SiCH3 4 times. So the given example is Al2CH3 6 times plus 2BF3 giving 2LF3 plus 2BCH3 thrice. So a halide reacting with the organometallic compound giving metal halide and ER thrice. So it's an example of metathesis reaction. The ligands are exchanged. So CH3 is exchanged with boron and F3 is given to aluminum, forming AlF3 and BCH3 thrice. So it's a metathesis reaction. The next question is treatment of SnPH4 with HgBr2 results in the formation of option A HgPH2 and PH3SnBr. Option B is HgPH2 and PHSnBr3. Option C is HgPHBr and PHSnBr3. And option D is HgPHBr and PH3SnBr. So this is an example of metathesis reaction. Uh, uh, Mr plus Ex giving Er plus Mx. So this is the Ex and this one is the Mr. So the reaction is SnPH4 plus HgBr2 will be giving HgPHBr plus pH3SnPr. So you can see why this one is not forming, because if in SnPH4 there are 4 pH present. So SnPH4 and HgBr2. So if we give 2 phenyl group, there will be 2 phenyl on 10 remaining. But in the option there is 3. So this is not possible. And in the second one, again 2 pH, then 2 pH should be remaining on 10. So it's again only one is given in the option. So this is also not the answer. Here only one pH is replaced for Br on SgBr2. So 3 pH should be present. Here only one pH is given. So again this is not the answer. And here one pH is replaced for bromine, and so 3 pH is remaining and 1 Br is exchanged. So this is the answer. So option D is the answer. Next question is hydrosilylation of alkene is an example of. Option is hydromethylation reaction. Option B is beta hydrogen elimination reaction. Option C is transmethylation reaction, and option D is metathesis reaction. So hydrosilylation reaction is silane reacting with an alkene. So one hydrogen is given to this carbon and a silicon carbon bond forming. So this is EC bond formation and EH bond breaking. So this means it's a hydromethylation reaction. So the answer is option A, hydromethylation. Next question is, the following reaction is an example of BH3O2 plus CH2 giving BH2 CH2 plus OR2. So we have already discussed this one. This is hydroboration. and the reaction is so one hydrogen is removed and given to the carbon, and one BC bond is formed, and this is removed. So the product is so BC bond formation and EH bond break. So it's a it these are the properties of hydromethylation. So the answer is option C, hydromethylation reaction. Next question is reaction of RMGX Grignard reagent with SOCl2 and SO2Cl2 yield. Option A, R2SO2 and R2SO. Option B is R2S and R2O. Option C is R2SO and R2SO2. And option D is RSO3 and R2SO2. So, the reaction of Grignard reagent with SOCl2 and SO2Cl2 is metathesis reaction. So, the reactions are RMGX plus SOCl2 gives R2 SO2 plus 2 MgC. And so in metathesis reaction, MR plus X gain MX plus ER. And other, so the answer is option C, R. With SOCl2 it forms R2SO, and with SO2Cl2 forms R2SO2. And other reactions of Grignard reagent are uh, with the checks it forms alkanes. With water forms again alkane. With RCHO and water forms alcohol, and with halides forms ERN. and with the carbonyls and water forms aldehydes, and with oxygen it forms alcohol. And here E can be boron, silicon, germanium, tin, lead, phosphorus, arsenic, and antimony. Next question is in CP star ZnMe, the hapticity of CP star group is. So in CP star ZnMe, the hapticity of a CP star group is option A, eta 2, option B is eta 1, option C is eta 5, and option D is eta 3. So the number eta, which is hapticity, predicted by 18 electron rule. In zinc, uh, D10 S2 configuration. So 18 electron rule suggests that in an organometallic complex, if there are uh, so 18 electron rule states in an organometallic complex, if there are 18 or multiple of 18 electrons are there, then the compound will be stable. In lower atoms like lithium, beryllium, and all, 18 becomes 8 electrons will be stable. So for zinc, 18 electron will be applied. So in zinc, there is 12 electrons present. And in methyl group, it will give 1 electron. And so total will be here 13 electrons. So to become 18, we need 5 more electrons. So 5 electrons will be provided by Cp. So the Cp should be giving 5 electrons. So the hapticity, so this is Cp minus. So if it gives 1 electron or from coordinating to 1 carbon, it means eta 1. And it gives only 1 electron. And eta 5 means coordinating to 5, and it will give 5 electrons. So this is eta 1 and eta 5 is, so this is eta 5. So this electron will go into the resonance, and there is 2 electrons in each multiple bonds. So this will be 2 and this will be again 2. So 2 plus 2 is 4 and this negative charge becomes overall 5. So when it goes into resonance, it will be eta 5, and when all carbon coordinates, it gives 5 electrons. So this will be eta 5. So 5 electron has to be from eta 5 coordination of Cp. So the answer is option C, eta 5. The next question is the reduction of 26 to C6H3 GaCl2 with Na yields species X, and it possesses the structure pi. And X and Y are, option A is X equal to Na2 26 mes twice C6H3 gallium thrice, and the structure is linear. And option B is Na2 26 mes twice C6H3 gallium thrice, and angular structure. Option C is Na2 26 mes twice C6H3 Ga thrice and bend structure. And option D is Na2 26 mes twice C6H3 gallium thrice, and the structure is cyclic. So the reaction to produce X is 326 mes2 C6H3 gallium chloride reacted with 8 sodium chloride, giving 6 NaCl will be removed, and it forms Na2 26 mes2 C6H3 Ga. So X is Na2 26 mes2 C6H3 and gallium thrice. The structure will be gallium in the cyclic form. So this is the structure. So and this is Y. So it's a cyclic structure. So answer is option D. X is Na2 26 mes twice C6H3 gallium thrice, and structure is cyclic. Next question is in BeCp twice. The hapticity of Cp is or are. Option A is both eta 5. Option B is eta 1 and eta 5. Option C is eta 1 and eta 3. Option D is both eta 1. So we can apply the 8 or 18 electron rule, and beryllium is in second period, and it's far left. So the number of electrons in beryllium is low. So beryllium is having 2s2 configuration. So only 2 electrons present. So to become 8 electron species, it need 6 more electrons. So 8 minus 2 is 6 electrons is needed. It will be provided from 2 Cp groups. So 6 can be obtained as 3 plus 3 or 5 plus 1 or 4 plus 2. So all three configuration is possible. So here we are given both eta 5. So 5 plus 5 is not possible. So that's not the possibility. And 1 and 5. So we have 1 and 5 here. So it's a possibility. And 1 and 3, it forms only 4 electrons, but we need 6. So this is not the option, and both eta 1. So in eta 1 only 1 electron present, and 2 eta 1 means only 2 electrons. So this again is not the answer. So eta 1 and eta 5 configuration is possible. So eta 1 will be so coordinating to this carbon will be eta 1, and eta 5 is coordinating to all 5. Next question is in tetramer of methyl lithium form. Option A is 2C 2E bond. Option B is 3-centered 2 electron bond. Option C is 3-centered 3 electron bond, and option D is 4-centered 2 electron bond. So we are given tetramer of methyl lithium. So we know the structure MELI 4 times. So the structure is cubic. And lithium and methyl group occupies in the alternate corners. So lithium in opposite corners, and methyl group also in the opposite corners. So from here we can see that lithium will be in a tetrahedral geometry. So we can see there is a triangular face present here. So carbon orbitals of CH3. So methyl is CH3. So in CH3, the sp3 hybrid orbitals will be like this. So carbon orbitals of CH3 is lower in energy compared to lithium. So bonding pair of electrons are primarily associated with CH3 group. So the interaction between an sp3 orbital from a methyl group and the 2s orbital of lithium atom will form 4-centered 2 electron bond. So in this phase, this methyl group will be forming a bond. So we can redraw. So if we consider this phase, it's a triangular phase, and the CH3 bonds like this. So it's a 4-centered 2 electron bond, because lithium, which is 3 lithium and 1 carbon. That's 4 centers. So the answer is option D, 4-centered 2 electron bond. Next question is in SPD hybridization. The orbitals involved are option A S px and dxz. Option B is S py and dx square minus y square. Option C is S pz and dz square. And option D is S pz and dyz. So in group 12 metal, they form linear molecular compounds such as zinc Me2, CD Me2, and SG Me2. The zinc. So they are all 2 center 2 electron bonds. And so the preference for linear coordination may be due to similarity in energy of outer NS, NP and N-1d orbital, which permit formation of collinear sp-d hybridization. So the hybridization of outer N S and these are the p orbitals and this will be the d orbital. So they are in same plane, so they can hybridize and form SPD hybrid orbitals. So this is a D set and this is a P set and this is an S orbital. So they will combine to form SPD hybridization. So option C is the answer. Next question is the hybridization at lead center and the structure of Me3PbCl respectively are. Option A is sp3 and 2d polymeric chain structure. Option B is sp2d and trigonal bipyramidal structure. Option C is sp2d2 and square pyramidal. Option D is sp3d and linear chain structure. So Me3PbCl is it has linear chain structure. So the structure will be so this is the linear chain structure. And so each lead has pi coordination. So it means it will be sp3d hybridized. So option D, sp3d hybridization and linear chain structure is the answer. And uh, there are other organolead complexes like CP2PV. So it forms a polymeric structure in solid state. And in gas phase, it's bend structure. And other organo lead complexes like R2PV. So they are dimer in solid state. And the structure is so it has a bend structure. It's not similar to ethylene. So the bend structure can be explained through the hybridization and bonding. So in maybe uh, So the hybridization is sp2 hybridization. So one unhybrid orbital which is weakened and three sp2 hybrid orbitals are present, where one of the hybrid orbital has uh, one electron pair and other sp2 has one electron in each. And similar to this, next lead will be having one unhybrid orbital and three hybrid orbitals. So here what happens is that a bond between the sp2 hybridized and unhybrid p orbital is taking place. So a bond is formed with p and sp2 hybrid orbital. So to accommodate this lone pairs, the structure should be this bent form, not this planar form. Next question is the treatment of beryllium chloride and cyclopentadiene sodium, which is so NaCP in diethyl ether leads to the formation of option A eta 5 CP, eta 5 CP Be and NaCl. Option B is eta 1 CP, eta 1 CP Be and NaClO2. Option C is eta 1 CP, eta 5 CP Be and NaCl. And option D is eta 5 CP, OET, VE and NaCl. So the reaction is B, beryllium chloride and cyclopentadiene sodium. So beryllium chloride is BeCl2 and cyclopentadiene sodium is given as NaCP. So the reaction will be B forming bond with Cp and Na forming bond with Cl. So Be Cp twice and NaCl. So this is the balanced chemical equation, and we are asked to find the hapticity. So the hapticity is we can calculate with the 8 electron rule. So it's eta in beryllium 2 electrons. So to become 8 electrons, 6 more electrons needed. So 4, 6, 3 plus 3, 4 plus 2 and 5 plus 1 configurations are possible. So we are given 5 plus 5, which will be 10 electrons, which is not what we need, and 1 plus 1 is 2, which is again not the possible one. 1 plus 5 is 6, so this can be the configuration, and we are given 5 and OET, so this is only 5 electrons, so this is not the possible configuration. So option C is the answer, where hapticity is eta 1 and eta 5 for C2. Next question is aluminum react with methyl chloride CH3Cl to give X, and X on further treatment with sodium gives Y. X and Y are option A AlCl CH3 twice and Al2 CH3 6 times. Option B is AlCl CH3 twice and AlCH3 thrice. Option C is Al2Cl2 CH3 4 times and Al2Cl CH3 5. And option D is Al2Cl2 CH3 4 times and Al2CH3 6 times. So this is a commercial method of synthesizing Al2Me6. So the reaction is first given alumina react with methyl chloride. So 2Al plus 4CH3Cl giving Al2Cl4 times CH3 4 times, and this reacts. So given this is X, and given X treatment with sodium gives 5. So Al2Cl4 CH3 4 times plus 6 sodium will give Al2CH3 6 times plus 6 NaC. And so the answer is option D, Al2Cl2CH3 4 times. And Al2CH3 6 times. And in the laboratory scale, the synthesis is alumina reacting with HgMe twice. Next question is the reaction Li4CH3 4 times plus SiCl4 giving 4 LiCl plus SiCH3 4 times is an example of option A, transmethylation reaction. Option B is beta hydrogen elimination reaction. Option C is metathesis reaction. And option D is hydromethylation reaction. So here the ligands are shared. So which means Mr plus Ex giving Mx plus Er form. So this metathesis reaction. In transmethylation, metal will be replaced with another metal. In beta hydrogen elimination, hydrogen in beta position will be removed. And the alkane will be formed. In hydromethylation reaction, EH bond will be broken and EC bond will be formed. So here the ligands are exchanged. Metal here M is lithium and R is CH3. E is silicon and X is Cl. So all the X is given to M. So here Mx is formed and Er is formed. So it's a metathesis reaction. So option C is the answer. Next question is the reduction of 2,6-MEs2C6H3 gallium chloride with Na yields species Na2 2,6-MEs2C6H3 gallium thrice, and it possesses the cyclic gallium thrice unit. The cyclic gallium thrice unit holds an aromatic system with option A 2 pi electron, option B 4 pi electron, option C 6 pi electron, and option D is 8 pi electron. So the structure we have seen this previously. So gallium in trigonal planar coordination. And this system is aromatic, and so in the structure itself we can see there is two sodium, so one sodium will be plus one, so two sodium means two plus two charge will be there. So two positive charge means there should be a two negative charge present on this whole system. So that means there is a 2 pi electron present in the system. So option A, 2 pi electron is the answer. The next question is, in case of ALX3, where X is MECl, H and pH, tendency of forming bridging complexes is in order of option A, Me greater than Cl greater than H greater than pH, option B, Me less than Cl less than H less than pH, option C, Cl greater than H greater than pH greater than Me, and option D, Cl equal to pH equal to Me equal to H. So the tendency towards bridging structure is in the order Pr2 minus is highly favored, then halides, then hydride, then phenyl group, then alkyl group. So it's this order is due to the high electron density and ability to provide electron to aluminum. So we are given Me, Cl, H and pH. So X here is Cl. So X minus has more lone pair compared to other three. So it will be able to form a bridging bond more than these three. And in hydrogen, it's smaller and it's easier to form bridging. And when comparing phenyl and alkyl group, phenyl has a p pi bonds in aromatic uh, compound, so it can interact with the sp3 hybridized orbitals of aluminum. So the structures will be aluminum is sp3 hybridized, so in chlorine it has lone pairs, so highly electron dense, so it can form uh, the bridging bonds easily on aluminum. And similarly for hydrogen as well, in case of phenyl group, so it has p pi bonds, so the pi bonds will be aligning like this, so it can interact with these sp3 hybrid orbitals more than so this bond will be stronger. And in methyl group, so sp3 hybrid orbitals of carbon. So this p pi sp2 hybridized interaction is more stronger compared to this sp3 sp2 interaction. So the order will be Cl minus greater than H minus greater than pH greater than Me. So the answer is option C, Cl greater than H greater than pH greater than Me. Next question is, in the structure of Me3SiO Si twice O, the flexibility of SiO bond is due to option A, 3p orbital of silicon and 2p orbital of oxygen interaction. Option B is 3d orbital of silicon and 2p orbital of oxygen interaction. Option C is sigma star of Me3Si interact with the pi electrons present on oxygen. Option D is pi star of Me3Si interact with the pi electrons present on oxygen. So in Me3Si2O, the oxo-bridge organosilicon compounds have extensive delocalization of electron pairs over silicon empty orbitals, and sigma star of Me3Si interact with the pi electrons of oxygen, and it's called as negative hyperconjugation. So this transfer is oxygen 2 pi 2 sigma star of Si Me3. And due to this transfer from oxygen to sigma star of Si Me3, the Lewis basicity of oxygen decreases. So O becomes less Lewis basic. So that's all for today. This is the last assignment solving session, and thank you all for listening, and wish you all the best for the examination. Thank you.